Hi everyone, welcome to this video series on word embeddings used in natural language processing. In the previous video, we talked about the intuitions and the background on word embedding as a general topic and also outlining intuitions on word to vec. In the current video, I'm going to be talking about the training process, how we train a word to vec model using a neural net. So before we talk about the training of the word-to-vec model, I will be also talking about the embedding layer, which is a general embedding layer essentially. And I'll show you a Python code using TensorFlow and Keras, how general embedding models are used, um, let's say for text classification purposes. And then we will see the embedding models being used in the training of a word-to-vec model as well. Let's begin the nuances of a training process for word-to-vec model. First, I'll give you some examples of how we prepare the data set for the training purposes. For example, this is the sentence here, the quick brown fox jumps over the lazy dog, and how we extract the training pair from these sentences or from this sentence for the word-to-vec model training. So let's make an assumption. The window size is 2. That means 2 words before and 2 words after. So for example, for the first one here, if the target word is D, so there is nothing on the left hand side. So on the right hand side, these two become the surrounding word or the context word. Now imagine the window is sliding towards the right side, and this becomes the center word. Then the left hand side, you have the as the context word, and these two again become the context word on the right hand side. Then the sliding window moves to the right, and this is the center word, and these two become the words in the preceding, and these two words follow the center word. Now, this is the training pair that we will be using to train the word-to-vec model. So the idea is, imagine we have a sliding window of a fixed size, say n is equal to 2, and the word in the center is target, and those on the left and right side of the word is called context word. So for an easy understanding how we prepare the data samples, let's say we have a sentence, he says, make India great again. If this is the sentence, then what are the training pairs? The window, let's say we have the window is 3 on the left and 3 words on the right hand side. So essentially, for the first word, he, there's nothing on the left hand side. So no tokens on the left hand side, but these three become the um, the context word for the target he. Now the window is sliding, so next word is says, and on the left hand side, the window size is 3, and you have one word here, and window size is 3 on the right hand side, so these become the context word. Likewise, the sliding window moves to the right. Now you have 3 words on the right hand side and 2 words here on the left hand side, and there is nothing as the third word on the left hand side. Now the window moves to the right and India becomes the center word. So now you have these three as, or these two as the context word, and these three are your context word on the left hand side. And this is the idea of sliding through the text and extracting the data set or pair, training pair. Now for this given window, where he is the target and says and make and India or the context word. In case of skip-gram architecture, where the center word is he input, that means you're passing this as the input to the model and predicting the context. And that is what is your skip-gram architecture. On the contrary, in the continuous bag of word, the input is the context word, let's say says, make, India, and he is the prediction. So the training samples that we will be using in this case of skip-gram architecture, he and says would be a pair. So this is like X, for example, input, and this is the prediction. So he again and make, he again and India. Likewise, in the continuous bag of word, the input is X and output is the center word. So these are your context word as input, and the output is he in the continuous bag of word architecture. So the architecture of a typical word to vec, you're going to provide some input, and this is the input for continuous bag of word. For example, the window size is configurable. You can decide the window size, n is equal to 2, 3, or 4. Now, when you pass this as input, it has to be converted to a random embedding first. So this is called embedding layer. To the neural net, we will pass this randomly initialized embedding for each of the input word or input token. Now, next, what we're going to do is aggregation because you're passing multiple tokens as input. We will aggregate them into one averaged vector, and that's a single vector representation for all of the input here. Standard neural net or multi-layer perceptron with one hidden layer for nonlinearity. And the loss function is a categorical cross entropy because we are talking about multiple predictions. In fact, as many words you have in the vocabulary, those many classes will be predicted. Let's say you have 500,000 vocabulary. So the input is going to be 500,000 and output also is going to be 500,000 classes. So we're going to use categorical cross entropy. So this is the softmax function that we use in case of more than two classes. So the same softmax function is being used here. So just for illustration, let's say this is the input context word and prediction is the center word or the target word is R, and then we use a softmax activation function. Okay, so let's move on then. As in the illustration, the input given our window from the previous example, let's say this is a window. So our input context word for CBOW model would be these three here, says, make, and India. So this is my target, which is Y, and these are my input. So says, make, and India are my input words, and the target word is the prediction that you want to predict. So essentially what we're saying is the says has strong association with he, make has strong association with he, India is also associated with he. So this is the semantic relation that we are trying to um, feed into the neural net. Now, where is this or how this embedding layer comes into the picture? So embedding layer is nothing but a table and a lookup table where you have dense representation for each of the row. So that means each of the row is going to represent the word. So for example, let me draw a simple picture. So let's say this is the table of, let's say the vocabulary size is 50,000. And each row is for one word. And here the number of dimensions of the embedding, let's say, is 50. So there will be 50 columns. Now these values, so one vector will be for a particular word. Similarly, for this vector or for this word, that's the vector representation. So basically, we will use a randomly created embedding layer to begin with in the word to vec training, and then we will use the training process, essentially the learning rate and gradient descent, to optimize and adjust the values in the embedding layer. So this is like a parameter table where each word is assigned to a row, and that row represents the dense vector. Now, dimensionality of the embedding is something configurable. So we can choose the dimensionality to be 50 or 100 or 300 or even 1000 or 2000, depending on the complexity and the variety and the diversity of the data set. Experimenting with different embedding dimensions is a crucial part of your project to determine what's the optimal value for the embedding dimension. So essentially, the embedding dimension or embedding layer will look symbolically will look like this. Let's say arbitrarily, these are your words, and each row is the vector representation for the word on the left-hand side. So the weights associated with the embeddings are initially randomly assigned or randomly created, and then through the training process or a back propagation, these weights are iteratively adjusted. And ultimately, the embedding layer will settle for minimum loss, and that produces the semantic representation for the words. That means the similar words will have similar embeddings. Next, I'm going to show you a classification example, IMDb movie reviews classification example, and there I will explain how embedding layer in Keras actually functions and how we are going to use that for the purpose of sentiment analysis or text classification. Yeah, let's begin the coding for text classification. So this example is going to be, using word embeddings.